Thank you very much. Good morning, everyone. It's really, really good to be back in beautiful Yash. I've been looking forward to this a lot. And I'm here today to help us explore the fact-based realities of AI-assisted coding. And in this presentation, we're going to cover the good, the bad, as well as the slightly ugly side of AI. And we have a lot of ground to cover, and I want us to start by traveling back in time. I want us to travel back to 1977. And the reason I want to do this is because I recently got exposed to the promises of AI-assisted coding in a pretty unexpected way. You see, earlier this year, I picked up a new hobby. I wanted to write games for this beautiful machine. Does anyone recognize this machine? Some of you, not that many. This is an Atari 2600, developed in 1977. And when you start to code on that machine, you will notice that it's pretty constrained. The first thing you notice is that you have to write all code in assembly, right? There are no higher level languages. The other thing you will notice that is a little bit concerning is that there is no operating system. So you have to do all the basics yourselves, right? Inputs, output, all of that stuff. So it's pretty effortful. What surprised me the most was that memory, you have 128 bytes of RAM. That's not a lot, is it? The good news are you're fully compensated by 4 full kilobytes of read-only memory. So those are the good news. The bad news are you have to use that memory for not only your game logic, but for all the graphics and audio. So I have to admit, I struggled a lot with getting something going here. But eventually, I managed to wrap up my first game, and I pushed it to GitHub. What happened then was that once I pushed my code to GitHub, I get this ad where it says that you can code 55% faster using Copilot. So I thought, interesting. That stuff really works on an Atari 2600? And then some more existential questions, like, can Copilot make me 55% faster at my hobby? Do I really want that? What do I do then? Do I pick up another hobby? I mean, all these questions, right? And I decided to dive a little bit deeper into this. So let me ask all of you, how many of you have heard this claim of becoming 55% faster? That's like half of you, maybe. How many of you have read the research paper that claim is based on? Not as many. So let's look at this together. So that claim comes from a paper published a couple of years ago by Microsoft and GitHub people. And it's a pretty good paper, and it's very good in the sense that, like all good research, they're very clear about the limitations and the constraints. And I want to highlight some pieces of information for you here. You don't have to read everything. I'm going to walk you through the highlights. First of all, the effect seems real. Indeed, some people get 55% faster, but they get 55% faster on the tasks that were studied, which were pretty much classroom tasks. So the researchers are very clear that there's no guarantee that this productivity benefit expands to, the task we do as part of being professional software developers. They also pointed out that the ones that benefit the most from a tool like Copilot are the less experienced developers. That's where they saw this 55% effect. For senior people, the impact levels off. And finally, the last thing, the thing that really, really worried me, was that they make it very clear that this study does not examine the effects of AI on code quality. So that got me thinking a lot. What is the effect of AI on code quality? And does it matter? Is it important to us? And I've been doing a lot of work in that area over the past year. And then finally, just a couple of weeks ago, there was a new paper published. And this was a massive, massive study. It's that type of study I can only dream of doing. It was done on more than 4,000 developers, studied in a real setting, developing real software. And now, the numbers were a little bit lower. But even here, there was a real productivity benefit. This time, they claim that you can complete tasks 26% faster. So that's still a significant gain, isn't it? Right? However, what's so interesting here is that the study points out or claims that there were no adverse effects on code quality. So this is basically acceleration with maintained quality. Isn't that beautiful? It is, it is. And then you read a paper, and you're curious, what did they use to measure code quality? And it turned out what they actually measured was build success. So nothing wrong with measuring build success. It's good that our software builds, but it's a pretty low bar for quality, isn't it? Right? So I like to claim that we still have no idea how AI impacts code quality. And we have to be really careful. Because if this effect is real, that we are completing tasks faster, it simply means we're able to write more code faster. More code of an unknown quality. What are the implications? That's what I want to study. And I'm going to cover this from two different angles. The first is the human motivational aspect, and the second one is like the more financial productivity perspective. And for the human motivational perspective, I don't think anyone has framed it better than Mr. Kevlin Henney. So he has this beautiful, beautiful quote where Kevlin said that using AI, what we have done is basically we have turned all ourselves into maintenance programmer, right? We took all the nice and fun and creative stuff out of programming, and we're now left in a position where we have to understand code that someone else wrote, in this case a machine. And that's arguably a much, much harder task than writing the code in the first place. So there's this aspect of it. The other thing I really want us to focus on today is that I want us to question, are we focusing AI on the right problem? And to explain what I mean by that, I want you to have a look at this graph. So this is a graph from a piece of research that looked at where do we developers spend our time. And today's AI is very much focused on helping us write more code faster, new code, right? But if we look at this diagram, we see that writing new code, that's a very, very small part of our day job. It's roughly 5% of our work week. So being 55% faster on 5%, that translates to roughly like 1 hour saved per work week. That's not bad. 1 hour is 1 hour. If I had an extra hour, I can spend more time on Matari. That's always nice. However, it's not groundbreaking. It's not that disruptive. Instead, if we look at this research, we see that the big win is here, 70%. That's the time we spend trying to understand the existing code, trying to understand what's already there. And as we learned in the keynote by Michael, this is a really, really important part. So what if we could rethink AI and start to use it to help us understand code instead? If we do so, we unlock a really large potential. Because why settle on becoming 55% faster when you can become 10 times faster? And I know this sounds like an absolutely ridiculous claim. That's why I'm so happy to have data to support that statement. So please have a look at this graph. This graph is from a research paper that me and my colleague, Dr. Marcus Borg, published 2 years ago. And it's a paper where we looked at how does code quality impact development speed. And I'm going to talk a little bit more about how we measure quality later, but basically all you need to know for now is that we use a metric called code health that can split code into 3 different categories. You have green, healthy code that's easy to understand, yellow code, that's problematic code with technical debt, and then you have red code, and that's the type of code you never ever want to have to work with. So what we see here is that if we have green, healthy code that's easy to understand, we can develop new features or fix bugs 10 times faster than people that are forced to work with red code, right? So code quality is very important from a productivity perspective. What does this mean for AI-assisted coding? It simply means that when an AI accelerates the creation of new code, we really, really want to make sure that that code is healthy. Because if it's not, we're creating a massive friction point for us. So let's look a little bit deeper at the research. I already told you about the risk. If we have an AI that creates code of poor quality, it's going to make us slower because the majority of our time is spent trying to understand that code, right? But there's more to it. In another follow-up study that we did, we also looked at onboarding time. How long does it take you to fix a bug or implement a new feature, depending if it's code you have worked on before or if it's code you have never seen before. And of course, code quality is something that impacts the onboarding curve massively. It can actually take you twice as long to onboard yourself in more problematic code than healthy code, right? So what's the takeaway here? The takeaway from me here is that the way I view AI is that the big win for us is to use AI to optimize for software maintenance, to optimize code for understanding. And that's known as the process of refactoring. So how many are familiar with refactoring, the concept? That's a clear majority, very good. So refactoring at the surface is simple. It's about improving the design of existing code without changing its behavior. However, even as fundamental it is, it actually means that when we change code, then it's not the refactoring unless we improve the design. How do we know if we improve the design? We need to make that very objective if we want to use AI to do that, right? So we need an objective way of knowing if one piece of code is better than another. The second implication is that it's also not a refactoring if we fail to preserve the behavior of the code, right? Because if we fail to preserve the behavior, then we have introduced a bug. And if we violate any of these two properties, then we're not doing a refactoring. We're doing something different. And I think the technical term for that is a refactoring, right? So to study this, me and my team set out and did a large-scale study, and we have published a paper on it. You will get the link to it. The paper is called Refactoring versus Refactoring. And what we did here was that we used AI to automatically refactor code and measure the outcomes, and I'm going to walk you through the results. Before I do that, I want to cover these two challenges of refactoring. First of all, how do we know if the code improves, right? To do that, we use the same metric as we use for these code quality studies. So we use the code health metric for that. And I want to give you a high-level introduction to how it works. So first of all, code health is a file-level metric. So you take a piece of source code, you parse it, and then you analyze it for a couple of code smells. And the more code smells you find, the worse the code health. And these code smells are split broadly into 3 different categories. So at the top level, you look for things like module level issues, class design issues. And to give you just one example, we might look for things like low cohesion. So who's familiar with low cohesion? Who knows what that is? It's like a third of you, maybe. Good. So low cohesion, I like to think of it as, a class that has too many responsibilities. So maybe you have stuffed too many business rules into the same class. And now that code becomes hard to understand, because when you read that code, you need to understand all these different business concepts to make sense of it. It's also dangerous because the more responsibilities you have in a module, the higher the risk for things like unexpected feature interactions, right? You change one piece of code and you break an unrelated feature. Those are some of the worst bugs we can ever have. So low cohesion is a big problem. Then at the function level, we might look for classics like copy-pasted code, right? Or GAD functions. Has anyone heard about GAD functions before? Some of you. You've probably all seen them. So GAD functions, they are large, really long functions. They contain a lot of logic, a lot of if statements. And the reason for that is because, again, they are low on cohesion. They have too many responsibilities. And as a consequence, a GAD function tend to kind of center the behavior of that class. So each time you want to make a change to that class, you end up in the GAD function. And over time, it just becomes more and more complicated. So it's a big problem. And finally, at the implementation level, the code health metric looks at various complexity patterns. And to give one prominent example, we look for things like nested logic. So that's something you have all seen. So nested logic is simply when you have an if statement, inside an if statement, inside an if statement, and then a loop for good measure. Ever seen code like that? What's the problem with it? Problem with it is that it plays pretty poorly with the human brain. So it kind of overloads our working memory. And consequently, there is some very good research that shows that roughly 20% of all programmer mistakes are due to deep nested logic, right? So we measure all these things. And depending on what we find, we have algorithms that can score and categorize every single piece of code as being in one of these three categories. So green, yellow, or red. And when code is yellow or red, it's never only a single factor. It's always a combination of these code smells. Did I manage to explain that? Good, good. So now we have something that we can use as a gold standard to tell if one piece of code is better than another. And armed with that, we set out to benchmark a bunch of popular large language models on refactoring tasks. And we used a data set of more than 100,000 refactorings. And I want to show you what we found. So first of all, the way you read this is that to your left, you have the large language models that we used. And the first column, valid code, simply checks, has the AI generated syntactically correct code? And we see that, yes, most of the time they really do this, right? The AI seems to be really, really good at generating correct code. So that's good. The first big drop-off comes in the next column that says code health improved. So this is where we check, is this a refactoring in the sense that the code improves? And here we see that in roughly 1/3 of the cases, the AI fails to improve the code. So they're doing a refactoring, right? They give us code back that's different, but doesn't really solve the problem. And finally, the largest drop-off comes in the last column, where we check, is it a valid refactoring? And the way we checked that was by that we only included code that had good unit test coverage, so we reran the tests. And it turns out that in the majority of the cases, 63% of the cases at best, the AI will break your code. Isn't that fascinating that the LLM is more likely than not to break existing code when asking it to refactor it? Think about it differently. Sorry. Let's say that you had a colleague. They would break your code in 70% of all changes that they do. Would you be happy? My guess is that they would be asked to look for new challenges promptly. But for a machine, we somehow accept this. However, there is a little bit of light in the AI tunnel, because looking at these numbers, it's pretty depressing. And I'm well aware that this study, we collected the data almost a year ago. So I know that there are new large language models, and we have kept this up to date. And the new large language models, they perform marginally better. They are typically slower, but they perform a little bit better, but it's nothing dramatic. So for all practical purposes, this is the state of the art still. However, I happen to have a team of optimists. So when we looked at this data, we thought this is actually quite good news. Because if the AI can do correct refactorings in 37% of the cases, it actually means that we could fix 37% of all the application code technical debt out there. The trick is only to know which refactorings are good and which are the bad ones, right? So we can filter out the bad ones and keep the good. And we decided to build a solution around that and see, can we do this? And I want to walk you through the high-level solution, and then I want to show you a demo to see what it looks like in real life. So first of all, this is what happens. I, as a developer, I work on some code. I write some code, and I might find that, okay, I could actually simplify this. So I ask the AI to do this. However, my request for refactoring doesn't go directly to an LLM. We have a step in between. And this step in between is something that we call a contextual model selector. So what's the purpose of that thing? Well, the thing is that when we did this large benchmarking study, we noticed some patterns in the data. We noticed that some LLMs are better at refactoring certain types of code than others. So that made it possible to build a simple machine learning model that can select the best LLM for the job. So in this case, the model selector might see that, okay, depending on the properties of this code, maybe OpenAI can do a good job with it. So we send a request to a specific LLM. The LLM will always respond, and it will always respond with confidence, right? But here we know that 2/3 of the refactorings we get back are broken. So what we do now is that we add a fact-checking layer, or a validation layer if you want. And the first thing we check is, has the code health improved after refactoring? If not, then we discard it. It's not a refactoring. Then we also try to do a certain level of semantic validation to check, is this code still likely to do the same thing as it did before? And if it passes that gate, then it's good. If not, then again, we discard the solution. And then we might go back and try another LLM and see, can that one solve this problem? And if we get something that passes these validations, then we have something that we can propose to a user as a better way of implementing that code. So we can propose a refactoring. Now, I'm going to show you some numbers on this, how much you can expect an LLM to improve. Before I do that, I want to show you a couple of demos so we can see what an AI actually does when it refactors code. And I want to show you an example on our real-world code base. So this is one of my favorite code bases, Glovestone. Anyone familiar with that one? So Glovestone is a lightweight Minecraft server implemented in Java. And it's a code base with a rich history, so there's a lot of code there. And what you see here to your left is a visualization of the code base, where you see the different files as circles, and the colors show the code health of the respective parts. And we see there are 2 big hotspots with red code, right? So this is highly problematic code. So what I want us to do is to look at some of that code. What do you think red code looks like? Here it is. What a beauty, isn't it? It's quite interesting because this type of code, where you don't really need a code analysis tool to tell you that you might have a problem, you can really just look at the shape of it, right? And to make it clear, what you see on screen is only a small part of the code, so I think it deserves a little bit more attention. So let's scroll it through. Have a look at this. There's more of it. Don't worry, still have a little bit to go. Here we go. That's it. So question to all of you. How long would it take you to refactor this code? And I mean, even if you wanted to, where would you start? And of course, what could possibly go wrong when we try to do that, right? So let's see if the AI can help us out by giving us an actionable starting point. So what I do now is that I use a Visual Studio plugin that can highlight the code smells. You're going to get the link to that one. It's a completely free plugin you can use. So I see here that one of the code smells we have here is deep nested logic, right? You see that with the nesting. So if I click on that one, then I get a button here. I press the button, and under the hood, all these steps happen. Right now we go to an LLM, we get some data back, we validate it, and we present it. But what's interesting here is to look at what did AI actually do to our code. Well, what it did was that it seems to have identified a responsibility in the code. This large chunk of logic there, and they had simply taken that code, extracted it into a new method, and put a descriptive name on it, right? So what I like about this is that the AI even managed to figure out and describe what the code does. It's initialized the graphics, right? So we now have that reflected in the method name. And this is, to me, one of the big, I mean, so far I've been talking about all the drawbacks with AI, but one of the big benefits is that the AI is very good at one thing we humans are traditionally not so good at, naming things. It's really, really good. So this is a nice first step in cleaning up the code, and now I can see that the rest of the code suddenly looks much, much easier to reason about. But maybe this was a too big initial example to actually see what's going on. So let's look at another opportunity to refactor, and let's try a much simpler refactoring so we can follow it through. Here's another piece of code. No deep nesting this time. And this code, it's much, much easier to reason about, right? But it's not trivial. And when we start to work on it, it's very easy to get something wrong because there's still a lot of complex logic. So this is the complex method code smell. Lots of conditional logic in a single method. And again, what I'm going to do here is that I'm going to ask the AI to refactor this code. So I send a request to the LLM, I get something back, and I validate it. And yeah, I can diff the code, and I can see what did it actually do, and I see that again, it seems to kind of break up, identify the different responsibilities, break them out, encapsulate them, and put a good descriptive name on them. Another thing that you might not have noticed, but in this prototype, what we also did was that we provided the details of the fact-checking. So you see here at the top that you can see the outcome of that fact-checking. You can see that here's a statement that says that this refactoring will improve the code health. The code will become easier to reason about. It's also likely to preserve the semantics of the code. So that means I can now apply it, and when I do, my code smell goes away. So that means I could move from the code here to the left to the code on the right. Now, I want to be very clear about this, that this code, is that the best possible solution? Is that the code we would write ourselves? Maybe not. Is it better than the code on the left? Yes, it is. And I think that's the point of it, that we can go from the mess on the left to a much clearer representation on the right, and that completely changes the game. Because I actually think that you don't even have to be a programmer to be able to tell roughly what this code is about, right? You can just read the names. And that's the power of refactoring. Code should be really, really simple to read, and it should reveal its intent. So in that respect, I think AI is extremely helpful to us as developers. Now that you have seen a couple of examples on how this can look in the real world, I want to look at the facts behind it. How well does it actually perform? Is it an improvement on top of the LLMs? So what we did after building all these layers around the AI is that we redid the benchmark. And what we found here is that we can actually elevate the precision, the correctness level of the refactorings we get to 97, 98% correctness. So what does that mean? Does that mean that if I do 100 refactorings, 2 of them will still be broken? Yes, that's exactly what it means. However, what I want to point out that 98% precision actually exceeds the performance of even human expert programmers. So by using LLMs with fact-checking and validation techniques around them, we can actually elevate AI to a point where it outperforms human experts. And this obviously raises a number of questions. First of all, if we have a refactoring technique like that, couldn't we just use AI to rewrite all code at once, right? You know, we have all seen these legacy code bases, right? What if we could just drop in a tool and it would crawl through it and simplify all the code? Wouldn't that be a good idea? I'm a little bit skeptical. And again, I think this ties back to the keynote Michael did this morning, because it's very much about learning. Specifically to me, it's about balancing short and long-term goals. So I want to tell you about a study I read about a couple of months ago. So this was a really, really interesting experiment. It was a professor, Mr. Klopfer. He did an experiment with his students. So these were computer science students, and what he did was that he split them into multiple different groups. And they had to get some basic problems to solve. And the first group, they were allowed to use ChatGPT to solve their problem. The second group weren't allowed to use AI at all. They were restricted to just old school Googling stuff. And then it turned out that the first group that could use ChatGPT, they completed a task much, much faster than the group that had to Google and search for the information themselves. So again, that kind of reinforces this claim that AI comes with a real productivity benefit. However, the beautiful thing is that Klopfer then did a twist on the experiment. What he did was that after they have handed in their solutions, he asked the same groups to solve the same problem once again, but from memory. And now the table shifted. Because now the people who had used ChatGPT couldn't complete the task at all. They haven't learned anything. Whereas the people that had to figure out the information themselves could easily reproduce that. It was trivial. And as someone with a psychology background, I think that this is it's a fun story, but it's also completely unsurprising. Because to learn something, we need to engage actively with the subject under study. There aren't any shortcuts if we really, really want to internalize the content. And I think that the key here with the Klopfer's experiment is that task completion doesn't necessarily come with true learning, nor with understanding. So the risk, if we just focus on the short-term goal of, completing our Jira tasks a little bit faster, is that we quickly end up with a massive amount of code that no one really understands. And the key thing to know about software is that the majority of the costs are not about creating the code in the first place. It's about what happens after the code is built. That's where 90 to 95% of the lifetime costs are. So I think it's really, really key if we use AI or whatever technique we use to balance these short-term goals, creating the first solution, versus making sure it's maintainable and sustainable. And for that same purpose, when it comes to using AI to clean up existing code and to refactor it, one of the principles I've come to value more and more is the principle of simplicity. So what does that mean? Well, it means that I see a lot of value in keeping the refactorings minimal rather than going for big rewrites of the code in the first place. Because I think it's the small stuff which adds up. And if we keep the refactorings simple, then we enable much faster review and confirm cycles from us as humans. And I mean, once we have cleaned up the code, what typically happens is that we transform the context. So we're now in a position where you saw some examples before from Glovestone, right? Where we cleaned up the code. And that puts us in a position where we can now start to reason about the overall algorithm. We can start to understand what the code does. And that opens up the door for much more advanced future refactorings. But the AI can be a really, really good first stepping stone to get there. So, if I speculate a little bit about the future, that's always fun to speculate, isn't it? Right? What I think is going to happen now is that for the coming decade, we're going to live in a hybrid model where a lot of code is created by both AIs and by humans. And in this context, it's very easy to mistake code writing speed for productivity. And as we have seen in this presentation, that type of acceleration just isn't useful if it's driving our code base straight into this brick wall of technical debt, right? So I see two things that we need to consider. The first is a set of guidelines that I've been using over the past year to help us succeed with AI-assisted coding. And the other is about reasoning about existing code. So let's start with the guardrails and talk a little bit about them. So I think when it comes to AI, I think a lot of it is about getting rid of the hype and start to see where are these techniques truly useful. And for that, we need to start by setting realistic expectations. Because typing just isn't the bottleneck in programming, right? So let's start with realistic expectations on where AI can help us and where not. Then also think it's super important to make code quality something that the whole business values. Because you're going to get more code faster and you want to ensure that that code is maintainable and it is understandable. So I highly recommend to enforce a minimum bar for both humans and machines. And finally, I think a lot of it is about the rising importance of understanding code over merely writing it. So if we use AI-assisted coding, we will have to spend a little bit more time trying to understand what the code does, right? But not just accepting it. And this is what I think is a key principle if we want to succeed with AI-assisted coding, that we should never, ever accept AI-generated code that we don't fully understand. Because if we do so, we are trading away a long-term future of a maintainable code base for the quick win of being able to close a task. The other thing I think is promising to me with AI is that we can actually use AI. We can refocus it on fixing existing code like we have seen in this presentation. We can suddenly fix all that technical debt that we never get time for. And this, to me, is a big win, because if we can elevate generative AI to the point where complex code smells can be mitigated with AI support, then we optimize for understanding. And understanding is the dominant human-intensive work that we have to do today, not just the narrow task of writing new code. And I want to leave you with a couple of references before I take questions. So the first two references here are to the papers I've been referencing. The first is the CodeRed study, which looked at the business impact of code quality. The second is the refactoring versus refactoring paper, where you can read about all these validations, what we did, and how we collected the data. And the tool I've been using for the code health metric is CodeScene. That's, of course, where I work. So if you're interested in code quality and stuff like that, please have a look at us, consider to support us. And finally, if you want to try this out on your own code base, then there's the free version of the automated refactoring plugin is available for VS Code. You can just go to that link and sign up for it and get started with it. And finally, a little bit of self-promotion, which I think is perfectly fine at a conference like this. If you want to know more about maintainable code and code quality in general, then you could probably do worse than reading my new book, Your Code is Crime Scene, 2nd edition. With that said, I want to thank you for showing up to my talk. I really value that. So thanks a lot, and may the code be with you.